Acids and bases are a really big chapter. It covers a lot of things, and one of the things that we talk about after learning about equilibrium of acids and bases is common ion effect, and that also leads to the formation of buffers, because both of these involve acids or bases and salts. So first of all, let's look at the common ion effect, which is a shift in an ionic equilibrium, which is caused by the addition of a solute. Okay, and so what that means is that when you have a weak acid or a weak base, it's going to be in equilibrium, as we have learned, an acid-base equilibrium. So once it's in equilibrium, you can of course shift the equilibrium forward or back, depending on what you add to it. So for example, if you add to this acetic acid equilibrium, if you add a little bit of sodium acetate, then the sodium acetate is going to give sodium ions and acetate ions in solution. So once you have those ions in solution, they're obviously going to change the equilibrium. And so, go back to your Le Chatelier's principle and think about how it's going to change. If you have acetate ions in the product and you add acetate ions also, it means that the equilibrium is going to shift back. If it shifts back, then the pH also is going to change. How so? Because if it's shifting backward, then you don't really have as much as hydronium ions as you had before. So which means now the pH is going to increase because you have less hydronium ions in there. So addition of a little bit of an acid or a base can actually change the pH of a solution. So let's look at an example, okay, for calculating for the common ion effect and see what happens when you add a little bit of salt. So calculate the pH of a 0.1 molar HF, which is hydrofluoric acid solution, to which sufficient sodium fluoride has been added to make the concentration 0.2 molar sodium fluoride. And then the Ka is given to us. So obviously we're dealing with a weak acid. And so here is how you get started. You have the HF plus H2O. You're writing the equilibrium equation for this. And you get hydronium ion and fluoride ions in the process. So what are your initial concentrations? Your initial concentration is what is given to you. So 0.1 molar of the hydrofluoric acid is given to you, and the fluoride ions is 0.20. Okay, so right here, all right, that was a sodium fluoride ion concentrations that were given. So that is this over here. As the equilibrium is being established, there are changes going on. So as the equilibrium reestablishes itself, HF is minus X, and then the products are going to be plus and then plus X. And so then therefore at equilibrium, you have 0.10 minus X, and then at equilibrium, this is plus X. So then we set up our Ka for all of this. And so Ka is hydronium ion and fluoride ion divided by the concentration of hydrofluoric acid. So that's what it is given to us. Ka is given to us. What we don't know, of course, is X. Okay, and so we're going to be calculating for X, but we are going to assume that X is very small. Okay, so which means that these plus X and the minus X, okay, become negligible for us. So which means this is the only X we have to worry about, which is really good. It helps us from, say, from solving quadratic equations. So anyhow, to calculate the X is this. So which means that the hydronium ion concentration, which is right here, this is also X, right? So the hydronium ion concentration turns out to be 3.4 times 10 to the negative 4 molar. So once the hydronium ion concentration is known, now you can calculate the pH, and the pH now is 3.47, okay, of this acid. And what you may want to do is, of course, you can calculate the pH of the HF solution without the sodium fluoride in there, and then you can see how much the pH has changed, okay, of this. So anyhow, that's how you would do the calculations for common ion effect. Just remember that you have to add the salts in the initial stage, okay, right here, and then the changes will be as they are, okay. Then we come to buffers, and buffers is kind of like a common ion effect as well, okay, because in buffers you usually make them by taking a weak acid or a weak base and then taking its conjugate base or conjugate acid. So they really are just essentially common ion solutions, okay? And so the key thing about buffers is that the pH of buffers does not change if you add a small amount of acid or base, and this is kind of a very important factor of buffer, okay? So that your pH is maintained no matter what kind of a reaction you do. Of course, you can kill a buffer if you add too much of an acid or a base, so let's not do that. You know, and if you want to do that, you can do that too, okay? And in some cases, it does happen if the pH changes drastically, but otherwise, the pH of the buffers remains constant, okay? Or not constant, but within a small range. So what do we do in lab is we make buffers to do reactions in a very controlled pH environment. So for example, our body is a whole buffer. And so if you want to see the reactions happening in natural conditions, then you may want to make buffers which mimic our, you know, blood conditions, because blood is the biggest buffer possible in our body. So then what we do is we can calculate the pH of buffers, okay, using our traditional ICE method, which is the equilibrium constant. And then what we derive from there is the Hederson-Hasselbach equation, okay? So let me take you through the Ka expression first, because this is what you are aware of. So Ka is then the product concentrations divided by the reactant. That is what we've done so far. So what we do then is we rearrange this equation to keep the pH on the left hand side, and so that's the rearrangement part, and then we take the log of everything, okay? And so remember, to calculate the hydronium ion, to calculate the pH, we take the log of the hydronium ion concentration, right? So what we did here was we took the pH out, we took the Ka on this side, and that's what the rearrangement here is. So pH is equal to pKa plus log of the anion over the acid, okay? And this itself, this is the same equation as this one. This is what we call the Hederson-Hasselbach equation, and this is really fantastic in calculating the pH of buffers. So pKa of the weak acid or the weak base, you will know already. So whether you have a base or an acid doesn't matter. So if you have an acid buffer, you will have a weak acid and its conjugate base. If you have a basic buffer, you will have the base and its conjugate acid, okay? So it depends what kind of buffer you're making. Anyhow, this equation is the key for making buffers. So how do we actually make the buffer? What you do is you select your acid and the base, whatever you want, and then its conjugate acid or a base, okay? So usually there is a list of acids that have certain ranges of pHs that you can get. So for example, acetic acid is usually around 4.3949, and then so there are some other acids and bases in which you can have a controlled pH range. So you look at that, and then you just get the salt of those acids and bases, okay? And then you decide to make your buffer. So those tables are what you consult when you need to have a certain pH range, all right? So that's the pKa data that you look at. Once you know what the pH is that you want, then you can get the Hederson-Hasselbach equation and you determine the ratio of the acid to the conjugate base that you need. Okay, so for example, and this is again a very typical problem for buffers, is if you need a buffer with pH 4.5 and you're using benzoic acid for this, which pKa is 4.19, then the ratio of the conjugate acid to base would be what? So in this case, it would be 2.04 to 1. And how do you calculate that? So you use the Hederson-Hasselbach equation. The pH is 4.5. The pKa is 4.19. And remember, pKa is coming from Ka. You just take the natural log of Ka. Plus the log of the conjugate base over acid. So by the time you do this calculation, you will get 2.04 is equal to, and remember you do the anti-log here, okay? So take off the log, and so once you do the anti-log, what you get is the conjugate base over acid. So what this means is your conjugate base should be 2.04 times more than the acid, okay, ratio in there. Now this is in moles, and so if you were making a 1 liter solution, those are the moles that you would need in there, okay? 2.04 mole of the conjugate base and 1 mole of the acid in there. So that's how you would make a buffer. So you can make more quantities depending on what it is. If you need a 2-liter solution, you would double these quantities. That's all. So let's look at a calculation. What is the hydronium ion concentration for a buffer solution that is 0.25 molar in acid and 0.6 molar in the corresponding salt if of a weak acid, and the Ka is given to us over here, 5.80 times 10 to the negative 7. So here is our equation, and very honestly speaking, for most of the buffer calculations, you should not need an equation because this is not an ice calculation anymore. You're going to be using the Hederson-Hasselbach equation. So all you need to know is what is your acid and what is your conjugate base, okay? So here you're calculating the hydronium ion concentration, which means that you don't know the pH, okay, of the solution. Ka is given to you, so you calculate the pKa of that, which is then 6.237. And then you have the base concentration given to you, 0.60 molar, which is the salt, and the acid is 0.25. So you have all the things that you need in this equation, and so pH will be then pKa, which is 6.237 plus the log of base over acid. Okay, so 0.6 divided by 0.250, which gives us 2.4. And so then pH is equal to 6.237 plus 0.380 log of 2.4. That's what it was. And so once you know the pH, you can then calculate the hydronium ion concentration. So this is the hydronium ion concentration in this buffer. So you can go back and forth, okay, with this. Of course, you can calculate the pH if the acid-base concentrations were given to you, which is what we did over here, is we calculated the pH first, okay, and then we calculated the hydronium ion. So whichever way. So in this calculation, what we're going to do is see how the pH changes or stays the same when we add a little bit of acid or a base to the acetic acid buffer. You could work with any buffer. We're just going to take acetic acid just for the heck of it. But in any case, so we'll see how the pH changes, okay, or not change. So here it is. In this example, we will take 100 milliliters of a 0.1 molar acetic acid plus 0.1 molar acetate buffer. Okay, that's what we have. The 100 milliliters matters a little bit later on. Okay, not right now, not initially, because the first thing we're going to do is calculate the pH. So the Ka is given to us, and if it's not, you'll find it in the tables, in the data tables. Ka is 1.8 times 10 to the negative 5 for acetic acid. So pKa then is 4.74. So then you calculate the pH of the concentrations that are given to us, which is 0.1 over 0.1, which is really 1. And so this is pH is equal to the pKa, which is 4.74. Okay, and that's the thing. If you have equal ratios of both, then the pH is equal to the pKa. All right, so once we know the pH, 4.74, now we're going to go ahead in the next slide, add a little bit acid and base and see what happens. So let's see how the changes are occurring. We're going to add 0.001 mole of hydrochloric acid, which is a strong acid. And strong acid means that it completely dissociates. And if you go back to 2-3 slides and you remember the slide that I showed you where we had an equation of acetic acid or hydrofluoric acid, okay, and you add a little bit of the acid or base, and the equilibrium is going to shift. All you need to do, okay, for writing an equation for this one, and it is a good idea to write an equation over here because then you can clearly see the changes, okay, that are going on, is that since you're adding an acid, the acid is going to react with the conjugate base to give you the acetic acid back, all right? And so which means you're actually shifting the equilibrium backward, but we are writing the equilibrium as forward, okay, just because we're adding an acid. So according to us, this is going to be our equation, and it doesn't really matter because all we need is the quantities over here. So here's the acetate reacting with the hydronium ions that we just added. So the hydronium ions we just added was 0.001 mole. Okay, over here. If the molarity is given to you, I would suggest that you calculate the moles of it because that will be a little bit easier to subtract and whatnot. The acetate ions that were originally present in the solution was 0.01 mole because it was a 0.1 molar solution but you had 100 milliliters of it. Okay, remember? So because it was 100 milliliter, you only had 0.01 mole. If it was 1 liter, you would have 0.1 mole. So here it is 0.01 mole of the acetate. And then you also had the 0.01 mole of the acetic acid. That's what you started with. And now you've added the acid to it. So the acid is going to react with the acetate ion and it will give you more acetic acid, which means that the concentration of the acetate should decrease. And if it is going to decrease, you have to subtract the concentrations then. So 0.01 minus 0.001 molar, okay, or moles, excuse me. So you have to subtract those two. On the other hand, the concentration of the acid is increasing, all right? And so here you have to add the two values. So 0.01 molar, which is what you started with here, plus the 0.001 mole. And so now the concentration has changed just slightly over here. So here again, you can also take moles, but you can also take molar concentrations here. With the new numbers, your pH is 4.74 plus the log of 0.009. And the M over here, you can use that as moles also, because essentially what you're doing is a ratio calculation. So whether you take molar or moles, your ratio is still going to be the same. Okay, and so once you do this calculation, the pH turns out to be 4.65. And if you remember from the previous slide, the pH was 4.74. It's also written over here. That's the original pH that we had. And remember, the pH is also was equal to the pKa. So really, it's not been a much change over here. If you added the acid, you just decrease the acetate a little bit, and so it's just, you know, 0.1 different. Now if you add a little bit of base, okay, which is a strong base like sodium hydroxide to this, now we're going to write the equilibrium a little bit differently. Acetic acid was on the right hand side before. Now our acetic acid is going to be on the left hand side, because that is what is reacting with the hydroxide ion. So the hydroxide ion is 0.001 mole and our acetic acid was 0.01 mole. And the new concentration here would then be the subtraction of the acetic acid, because now the acetic acid is reacting with the hydroxide ion, so its concentration will decrease, and the concentration of the conjugate base, the acetate ion, is going to increase, because that is where our equilibrium is shifted. Okay, and so it's kind of easier to write the equations in the direction that they are going, so it's easier for you to see where to add and where to subtract. Okay, so instead of keeping with the old-time equations, don't do that. It's much nicer to write the equation as a forward. Okay, so then we have our new concentrations, and you can see from this and this over here, our numbers are reversed, okay, for both of these, because now our acetic acid is less and our conjugate base is more. All right, so the conjugate base over acid, this is our new ratio that we have. And when you calculate the pH of this, it comes out to be 4.83. So you can see that the original was 4.74. With a little acid, it changed to 4.65, and base 4.83. Really not a whole lot of change. Okay, we are either 0.1 here or 0.1 on the other side of the scale, but not a whole lot of difference. And that is the advantage you have of a buffer. And even if you added 0.002 moles of the acid, you will see it doesn't change a whole lot, okay, as far as the buffer is concerned. So unless you really add a lot of it, then you can drastically change the pH by 1 unit, but otherwise it's going to be a small amount. And really, why would you want to add too much? Okay, I mean, when you're working with buffers, you want to make sure that the pH is maintained. So essentially from this PowerPoint, be able to learn what acid-base combinations are required to make buffers. So even if I give you a table and I ask you what combinations are best, look at the pKa's and see what two compounds would be really good to make a buffer, say of a pH 4 or pH 7 or pH 9, something like that. Okay, and then be able to do all calculations regarding buffers and the common ion effects also. And you can work the common ion effects using the Hederson-Hasselbach equation also. Okay, so I'll try and put some pen casts up there for you to do some calculations with that.